Hi everyone, Seven Investing founder Simon Erickson here, and we're talking about cloud computing this morning. This is a highly complex and technical industry, and so I'm very thankful and honored to be joined by Paul Teich. He's the principal analyst at Liftr Insights in Austin, Texas. He's also an expert in this industry, one of the smartest people I've ever talked to about for cloud computing. Paul, thanks so much for joining me here this morning.
My pleasure, Simon. Great to be here.
Paul, like I said, cloud computing is highly complex, and there's a lot of buzzwords going on right now. But at the 10,000 foot level, are there a couple of fundamental changes that you kind of see taking place in the cloud?
So actually backing up to maybe a view from geosynchronous orbit, really technical reference. We hear a lot about serverless, and we hear a lot about software as a service, and essentially there are four categories of cloud computing today. Software as a service, which essentially is a data migration. You're giving up your app to use somebody else's app. That app is based in the cloud, and you're paying for the app usage, and that's where you get your efficiency. Underneath that are platform as a service. And so platform as a service enables your developers to kind of string together Amazon's database or Google's AI or Microsoft's apps, right? And Active Directory, good example, right? So it lets you use bits of other people's services to kind of paste together an app without actually having to do all that programming development yourself. Underneath platform as a service, infrastructure as a service, IaaS, and you've got this emerging functions as a service, FaaS. FaaS is what we refer to as serverless computing, okay? Now, that's kind of a misnomer. There are servers in serverless computing, okay? But it's more, the difference is that IaaS is traditional programming. So you use your traditional developer environments, you load your operating system or use an operating system available to you in an infrastructure as a service instance. But everything else is up to you. So you're writing the app, you're using Python or whatever language you're choosing, and treating it just like your own server, but it's running somewhere else, and that's where you get your efficiencies, is somebody else is maintaining the server. They're powering it more efficiently, cooling it more efficiently, and that's what cloud is. You pay as you go. Pricing is, folks call it various things, on demand or pay as you go is the baseline pricing. And then you can do spot pricing or reserved instances to try and get better than the standard pricing. The programming difference in functions as a service is that you actually have to use the logic provided by the functions as a service, and it's not traditional programming. There are some limitations in terms of the complexity of the logic you can use. It takes retraining your programming staff to how to use functions as a service. And so while we hear a lot of new development is considering functions as a service, if you're doing, back up another step, if you're doing kind of a lift and shift, and you have a program that runs in a virtualized environment like VMware, which pretty much everybody does, right? Your options are to do just a complete lift and shift. You run VMware on your on-prem infrastructure. You would go rent an IaaS instance, infrastructure as a service, and just use VMware in an infrastructure as a service instance to migrate your app from your on-prem infrastructure or your hosted managed infrastructure into a cloud. To go to functions as a service, you have to refactor your application. And to go to platform as a service, you have to refactor your application. So it takes a bit of knowledge after, as you're migrating your apps after that first step. Now, the gotcha with VMware is that a lot of the benefit you get from renting cloud instances is by right-sizing the instance. And so you can get 2 cores, 4 cores, 8 cores, a certain memory per core profile, SSD or not SSD, fast network connection back to your S3 storage buckets. There's lots of options to tune what you're paying for in the cloud. However, if you do a pure lift and shift with VMware, what you're going to end up with is a big bare metal instance. And so it's kind of like trading hyper-converged infrastructure on-prem for hyper-converged infrastructure in the cloud. And so what we hear kind of is, yeah, it's great, I moved to the cloud, I'm on VMware, and I'm not seeing the cost efficiencies that I would be getting if I were to do some kind of refactoring. Okay, if I were to, not even go cloud native, but just let's say I recompiled if I'm on a compiled system, or if I'm using some PaaS services on an IaaS platform, I can be really smart about which services I'm using. But if all I'm going to do is a lift and shift, it's not going to be as cost effective as I thought. So that's kind of the basics of what's where. I'll say with PaaS, SaaS, FaaS, you really don't get much of a choice in terms of what you're running on. So the actual cloud provider, they provide the hardware that your database runs on. If you're using RDS on Amazon, okay, you have no idea what actual servers are running that storage system, and you don't care. It's platform as a service. They're just providing it at a price with a service level agreement. With IaaS, you have more control. And what we're seeing is while some just kind of like cloud, people jumped into cloud, companies decided to go all in on cloud. They're doing some repatriation now as they discover they're not getting the cost efficiencies they were supposed to get in some areas. We're finding kind of that same thing with functions as a service, as developers like rushed over to do functions as a service. They discovered there were some things they couldn't do. There were some limitations. We're cloud-based. We're a DevOps group, and we run in AWS. And we tried to go all in on functions as a service on Lambda, and it didn't work that well. Okay, for us there were some limits, and we have part of it running functions as a service, and part of it running as traditional instance types in IaaS. So I'll leave it there, and we can go any direction.
And so it sounds like kind of at the basic level, though, everything is as a service now. The goal is to kind of provide those resources and that infrastructure so that people can focus more on developing their apps, and then whether it's Amazon, Google, Microsoft, anyone else, they're going to take care of the behind the scenes work so you can focus on the things you really want to focus on.
With the exception of IaaS. Okay, so that whole focus on behind the scenes, you go one step lower as you move down the abstraction layer. So if I just want somebody to replace my payroll system, done. I don't need to write another payroll system ever. So many sources, that's software as a service. And you can find analytics packages as software as a service, but if you have a special need, if you're doing something that a lot of companies aren't doing, and that's what we find with artificial intelligence and analytics, some of these streaming applications don't, the state of the industry there hasn't evolved enough to have a package, an off-the-shelf package that does what a company needs. That's when you back up and you start looking at functions, at platforms, and then it's infrastructure as a service. And if you really need the control, infrastructure as a service is a great way to go. What we're seeing is, despite all the hype about moving away from infrastructure as a service to platform as a service to functions as a service, it's grown. The top 4 clouds, what we measure, have grown in complexity by over 40% since we started measuring about a year ago. And by that, I mean the regional growth, new regions that Google, Microsoft, Amazon, and Alibaba have lit up for their clouds, to new geographies they've enabled, and new instance types and new sizes of types. So that proliferation and complexity, we see a 40% growth in less than a year. We're frankly pretty stunned.
Yeah, and Paul, second question for you, with those large cloud providers that you just mentioned that are growing very quickly, are the offerings that they are giving out there, are those becoming somewhat commoditized, or are there certain things that they're doing to differentiate? What does Amazon have that Google doesn't have, that Microsoft doesn't have, that Alibaba doesn't? How are they standing apart from one another as they're a cloud service provider?
So first level of complexity is memory per core. So large memory spaces, we're seeing a trend toward more cores, and that's true for, so there's a couple of different axes here. So one is processor choice. You've got Intel versus AMD. Now increasingly ARM is starting to be a choice. So Amazon has shipped its Graviton 2, second generation ARM based processor. But really the choice is memory per core. The processors have fairly similar performance. We're going to be digging into that in the future. But if you assume there's some fixed deltas between ARM cores, Intel cores, AMD cores. The next thing is, do I need 1, 2, 4, 8, 16 gigabytes per core? And so the core count interplay with I need terabytes of memory. If I'm going to, for instance, if I need higher than 8 gig per core, I need to go to Microsoft, pretty much. Microsoft is differentiated in supplying very large memory per core configuration points. I thought I had everything on Do Not Disturb. So memory per core, we're starting to see some speed differentiation with Cascade Lake. So we saw everything kind of stalled under 3 gigahertz per core in terms of clock frequency. And so that's how they're differentiating. The other one's smart NICs. So as the clouds offload the hypervisor onto the smart NIC, kind of a sidecar processor. So there's this whole evolution of network processing, offloading the network stack, trying to get as much application performance out of your server as possible. And the extreme of that is that now, like AWS Nitro and Microsoft's Catapult cards, I'm sure Google has one, they haven't talked about it yet. And actually Alibaba has what they call Dragon X. So they all have these sidecar processors on the NIC, which now contain processors of their own. So they can go run the hypervisor stack, the root hypervisor off of the main server processor and give the application all of the performance it needs for its host operating system, if that's a choice, or the container and your application. So you have a bunch of different variables. The big ones I think are in the next 6 months are probably going to be memory space size, memory per core, and processor speed with Cascade Lake coming on. We'll see if AMD can. It's one area where they were at parity with Intel, although core performance appears to be very good, and memory per core seems to be really good. AMD was kind of stuck at that same kind of frequency as Skylake. And so we'll see if they can boost frequencies with Intel Xeon Cascade Lake. That answer?
Absolutely, it does. Keep going, Paul. Go ahead.
Oh, sorry. And pricing is also a bit differentiated. So they each have slightly different pricing strategies. They're not going head-to-head, one-to-one. We've actually done some interesting box and whisker, chart analysis. When you put hundreds of different instance types with 8 cores together and different memory profiles, and you start to kind of tease apart where their pricing strategy is. Google is a very simple pricing strategy. They're aimed at developers mostly, and historically. They're trying to go to enterprise, but I think the other 3 offer a wider variety of pricing, I guess, to appeal better to enterprises who want to fine-tune, their cost optimization, right?
So let's dig deeper into that a little bit, because I think one of the interesting things that you're doing at Liftr is what you're describing as public cloud transparency, right? You're able to see the hardware configurations that are running all those instances, all over the world, basically. And so to your point about Google is slightly different than Amazon, slightly different than Microsoft and everything else out there. What can you tell us that you're finding out there, Paul? I mean, what are the overall takeaways that you're seeing from what's getting deployed? This used to be very proprietary, right, of what kind of hardware people were using, but what are you starting to notice out there?
I think the biggest competitive shift is that the clouds are starting to derive value out of advertising that they're using alternative CPU chips, processor chips. So used to be, AMD was AWS was one of the first in, and they said, well, we'll offer it at a 10% discount, see if anybody bites. It was a value play. But as Google gets into it, as Microsoft is into it, it starts to become a more nuanced competitive arena where I think customers will start paying less attention to which processor choice they're buying. On the GPU front, it's funny because essentially Intel's got this one big competitor. NVIDIA doesn't have that particular market challenge, but they have a lot of small competitors. And they add up to kind of the same share that AMD is taking in the processor space. What we're seeing is the focus has shifted from, there's still a bunch of virtual desktops, virtual workspaces, workstations, stuff like that happening in one portion of the enterprise cloud market. And we just saw AMD move into that space with its new Radeon Instinct. But the real action, I think, is going to happen in inference processing. So just to back up a second, in the AI world, in the deep learning, machine learning world, we divide up the training task from the inferencing task. So when you're training a model, you're trying to discover what works, how to recognize a cat or a hot dog, to use trivial examples, right? And you're trying to look for, these things are looking for, combing through video for facial surveillance and things like that. They're very sophisticated tasks. Training a system to recognize something, whether it's text or video images or multidimensional patterns and other data, right, is essentially a supercomputing task. And NVIDIA still kind of owns that market. Google invented their tensor processing unit, TPU, as a way to try and offer an alternative. And I think that didn't work as well as they would have liked. It's hard to expose that programming to developers. So they only expose TPUs through TensorFlow. Recently, they've opened that up a little bit. I think PyTorch was in development and may have actually shipped by now. I need to go brush up on that. But so that means only 2 programming languages can use a Google Cloud TPU, whereas multitude of anything you want to kind of throw at an NVIDIA GPU, they've developed a driver for it. That's kind of the challenge AMD has in the market. And it's also the challenge that Xilinx and Intel have in the FPGA world. It's much more difficult to program these because you have to do a lot more work to get your code to run on it with the rest of the code you're writing in the cloud. Whereas NVIDIA has done a good job with making sure that the integration is fairly seamless. So we're seeing the movement away from general purpose GPUs. Seems really strange to say that. So graphics processing units, what NVIDIA sells, toward having deep learning specific cores. They have a tensor core in their latest generations. So the V100, the Volta generation, V100 from NVIDIA, and also the T4, the new Tesla thing, have these tensor cores in it that are specifically designed to accelerate deep learning tasks. Now the V100 is aimed at training tasks. The T4 is aimed at inferencing tasks, which is where AWS has introduced their inferentia. So it's an in-house design. It's all backing up a bit. I mentioned Graviton. Okay, so AWS has this thing you've probably heard of called Alexa. Okay,
heard of that.
Heard that. And what they've done, and they're public about this, is Alexa's deployed at such scale. When you have millions, tens of millions of people using the smart speaker services, right? There's many levels of deep learning associated with that. So first level is speech recognition. What am I saying? What are the words I'm saying? Second level is natural language processing, which says, all right, so what's the intent behind what I'm saying? If I ask for a sports score, what team am I asking for? Is it something I ask for habitually, things like that. Then there's the whole context behind, now that you know what I've said, you understand the intent behind what I've said, now you have to go find the information. Okay, so
right.
Multiple levels of deep learning models to go handle Alexa. And what they did was they designed their own processor, the Graviton, now the Graviton 2. And they designed their own inferencing accelerator called Inferentia to go power specifically Alexa tasks. And so they decided, well, and this is something we see from all the clouds, by the way, when they deploy something at scale internally to serve an internal software as a service function, and Alexa falls directly into that category, they start buying in such large quantities that it becomes not just an option, but an imperative to expose that capability to the public cloud, right? So even though it was, they deployed first with Alexa, they worked all the bugs out of it, and then they offer Inferentia now as an alternative to programmers who want to deploy inferencing at scale for their apps. The challenge there is they had to go the same route as Google went, and you have a limited selection of programming languages and model types you can run on Inferentia today. That'll, like Google, probably get wider as we go through time. But because it's not a general market thing, because it was specific to a certain set of deep learning tasks, AWS's challenge is to give it broader appeal. But the decision to, hey, let's push this into the public cloud in some regions is really a no-brainer. They're buying it at such scale, and if they're seeing the cost efficiencies, which for Alexa translates into precise inferences per second per watt. Okay, so it's a complex interplay of am I doing the thing accurately and fast, hitting a certain user experience, right? I understand which team I'm talking about because it's baseball season, and it's the team I always ask about when it's baseball season, right? Which is different than the team I ask about during basketball season. But it knows these things, right? It knows what kind of context sensitive, and it's doing that at an efficiency that my data center can serve a lot of these requests per megawatt. Okay, so anyhow, that's kind of the scale at which we're operating now, and it's kind of what a cloud applications developer and then the folks who manage that application are trying to take advantage of.
Fair enough. So it's purpose, if I can summarize that, overgeneralize this perhaps, it's purpose driven for the companies that are developing it, but then still an operations per second, cost efficiency for everybody else that's using those on the public cloud.
Absolutely.
On the models that you were talking about for AI, obviously the algorithms are getting very complex now, and everybody's wanting to use it for a different purpose. Are those constantly changing and needing to be retrained, Paul? And what is your opinion on FPGAs? You talked about field programmable gate arrays. You talked about Xilinx, so I've got to follow up on that. What are your thoughts on this as everything is changing so quickly?
So training is a fairly general task. Okay, you're sifting in terms of convolutional neural networks, which is state of the art today. CNNs, if you've heard the literature, it's synonymous with deep learning. There are other kinds, but CNNs are our go-to today. It takes a lot of number crunching, a lot of matrix math, and it really does look a lot like a supercomputer. You're using a lot of GPUs working in the same memory space to go make this happen. Where we're seeing FPGAs deployed is a lot like Inferentia, it's a lot like T4, it's on the inferencing side, where you've already developed a model, you know what you're looking for. It's a much less general task, and you can then tune a neural network. Prune is technical term. You can eliminate parts of the network and maintain, it's almost like JPEG compression for video, where what we call lossy compression. Where this video right now is using lossy compression. It's not showing me and all my full pixelated glory, but it's saving pixels where it can, and people can't really tell the difference. And that's a lot of what we do in translating a model that we've developed on a training system with a high degree of accuracy on that big bad training system. What we're trying to do is maintain a threshold of accuracy, say 95% for whatever we're looking for, and pull down our latency. Less time to get to that slightly less precise inference, right? Tune the power. We tune the time, we tune the power, right? So if I can run it fast, I have a better user interface, I also burn less power. And so that's the task that FPGAs are well suited toward, is they can handle sparse architectures, sparse memory architectures, sparse network architectures. You can custom build the connectivity into an FPGA that would be less some architectures would be less efficient running in a GPU. Okay, so the hierarchy is that CPUs tend to be the really less efficient to run models on, and that's why Intel and AMD are implementing deep learning instruction set extensions to try and boost that efficiency. GPUs built for matrix math, but they're built for doing a lot of the same thing and a lot of very similar memory access models. And so if you're using different kinds of memory access patterns, GPUs may not be as efficient as then going to an FPGA and a bespoke solution, okay? And it's that bespoke solution that ideally when you're doing enough inferencing at scale, that becomes an incentive to build your own custom chip. And so Inferentia is kind of halfway to building a custom chip. It's Amazon saying, I have enough of the same thing I'm doing, and I think it's mature enough that I know kind of some memory access patterns I need to handle and some processing patterns I need to handle. But I know those are going to still change over the next 2 or 3 years. Eventually, we'll get to the point which we have models that work, and they'll work over 2 or 3 years without needing to be retrained. We're not there yet at all.
Are they being retrained because more information's coming in, like location awareness, more stuff to feed the answers that the queries are coming in for?
Well, it's that as you gather more data, you start to get more of your edge cases. So if you look at driving, right, you can get all the simple cases, in a few months data collection. But then you have cases that only come up like once every year or two. Mm-hmm. Somebody driving into a deer or a cow, right? And so you have to actually record that data and feed it into the driving simulator. Edge data is a lot like that. You get a lot of data that's just normal, okay? And it continues to be normal and it's not exceptional. And you're looking for those boundary cases that just don't happen that often. Something fails, a sensor fails, a motor fails, sensors and actuators, right? And it's not the common cases that concern you. After your first year or two of data gathering, you're really trying to stretch to find the edge cases because those are going to be interesting failure modes. And so you continue to gather data and you continue to train your models because you don't have enough data yet. And so that's the challenge, is we're still in the early years of doing this. And even when you look at consumer habits, right, you look at buying habits and how they change over time, we only have a snapshot of the population for the past few years. Okay, and so look at, Google and Facebook have tried to do these studies where, hey, post a picture of you 10 years ago, right? So that they actually start to try and get an idea of how people age, right? And that's important when you're going back and you're classifying my photo collection. If you're classifying several decades of my photos and you want to group all the pictures of me, I look significantly different, say 2 decades ago. And so the training data really never stops. People's accents and how they change, or just covering different regional dialects. My voice, as I get older, will change, right? And so we're not done by any means in terms of training models that can actually stand the test of time.
Paul, shifting gears a little bit, something that has been very popular lately has been, I guess you could call it data monitoring, right? You've got all these companies that are trying to look at log files, web logs of people getting to websites for cybersecurity reasons, looking deeper and deeper into the stack to try to fix problems and bugs. You've kind of got this IT monitoring thing now. You've seen companies like New Relic with applications performance management. You've seen companies like Datadog, Splunk is big in this. All these companies are kind of trying to look at large amounts of log files to monitor things that stand out and flag those to be having actions taken on them. I guess the question I want to ask you is, we're talking a lot more now about edge computing, which to me seems very different from the standard way of how we've done things. Now all of a sudden you've got Internet of Things coming on, you've got more complex processors being kind of out there all over the place. Does this same process of monitoring and observing translate to edge computing, or is this going to be a completely different challenge that we're taking on?
It does translate. Okay. We have a huge amount of data streaming in from the edge. A couple of problems. We have new sensors and we have new networks, right? 5G is going to be a completely new network build out, new equipment, new software, and the scale and complexity means things will fail, okay? And even if they're not failing, they're going to have efficiency problems in strange new ways, okay? And so anytime you're writing new code, so none of these applications have been stable for 10 years, right? We're just writing the code now. And so I haven't met a programmer yet who is bug-free.
Right.
We do what we can, agile development, new techniques, but we're continuously analyzing code. Okay, is the code running correctly, and is the code doing what it's supposed to do? Okay, two different problems. Okay, I can have code that runs correctly and just does something slight bit wrong from what I really need it to do. Is the network up? Is the network connected? Okay. How is my network connectivity behaving in a mesh or some other network topology? How is that bit of code running in the cloud, at the edge, in the internet end in the IoT end nodes? And so the scale and complexity means this log data, which I don't think a lot of people are really mining effectively yet. They're gathering the log data, but they're not mining it well yet. And this is where actually deep learning, AI, analytic techniques will come into play, is that as we instrument all this data, gather all this data, we have to go back and examine the log files to look for those exceptions that I talked about. We're not really concerned with, hey, we're running normally, and that generates a lot of log file traffic, okay? But you have to get that, hey, we're running normally file volume to actually get that, oh, this didn't work normally here. There's some interesting, inefficiency or error that happened that I may only see once a week, once a month, once a year, right? And that's what we're mining for. And in a complex system, they're going to happen. The problems are going to be very difficult to go debug because there's so many different degrees of freedom in these new applications.
So we're basically putting on the peripheral vision. Now we're able to see this much where we were able to see this much before. And now we're trying to find the outliers, fix the outliers so that things do get back to normal more quickly.
Right, and it used to be a lot simpler. We run one app on one server in one operating system image, right?
Right.
So now we have apps all over the place. I mean, literally, you've got an app in the cloud. You've got an app in an edge node. Call it a base station, right? You've got an app running on a phone or an access point. And so, trying to debug what's happening where. Is it a performance problem in one of those nodes? Is it a performance problem in the network between those nodes? Is it something with the app itself running there? And it's just the complexity is literally mind-boggling. Humans are insufficient to go debug the new complexity that we're inventing.
Final question for you, Paul. Our audience at Seven Investing is mostly individual investors. We know a little bit about cloud computing. We are nowhere near as complex and into the weeds as you are about everything going on out there. But there's also a lot of coverage on this right now. There's a zillion headlines to try to make sense of. You're the expert in the field, though, and for someone who's really interested in learning more about the progress being made in the cloud, what are a couple things that you would recommend we keep an eye on? Or are there also certain things that aren't getting enough coverage right now?
I think actually cloud is in some respects overcovered.
Yeah.
As we're looking at our near-term situation, which is I live in Austin, Texas, and I'm kind of on self-isolating lockdown now. I hit a certain demographic and I have allergies and all that kind of stuff, which is almost impossible to live in Austin without, right? But what we're seeing is the cloud supply chain didn't really slow down compared to laptops and smartphones and other consumer electronic devices. The cloud has a couple things going. The scale, although large, is still small, order of magnitude lower shipment volume than smartphones and some of the other things we're talking about. And it's incredibly high value. So these are the value leads, 90% margin products that Intel, AMD, Xilinx, Dell, Lenovo, HPE, Quanta,Ywin, all the ODMs and OEMs, the whole chip supply chain, the fabs that are producing the chips. Server is low volume, high value, and we haven't really seen a slowdown. We've seen memory prices go up just a little bit, but as people hunker down at home, do more work from home, do more conferencing and communication from home, I think we'll see an uptick in cloud services, which is kind of a virtuous cycle. Again, it's kind of a secondary reaction to this really unfortunate, pandemic we're going through. But if you're looking for, we're seeing, the AMD and Intel battle play out, and at some point we'll see a viable competitor to NVIDIA. And so those are the things I would watch for. Cloud growth, regional cloud growth is a big deal in Europe, especially as enhanced privacy laws. So local data locality is prompting in-country cloud data center build out throughout Europe right now. And so that's something to pay attention to, is like Switzerland gets new sites, Norway, it's very country specific. And so that's prompting, some new build out. And I think it's just not going to stop. So it's a hot area to watch. And I think almost any part of it is interesting. So, obviously we play in infrastructure, but just watching software as a service growth and analytics growth is all fascinating in its own right.
It certainly looks like the investment in the cloud is continuing to go even higher every year. Again, Paul Teich, one of the experts in cloud computing. If you ever go to a cloud conference, go to attend his sessions. He will be on stage. I know he's always traveling, and it's just such an honor, Paul, to get a chance with you to chat here this morning. Thank you very much for speaking with us.
Simon, thanks for having me. Enjoyed it.
And thank you for tuning in. Again, we are here to empower you to invest in your future. We are 7 Investing.